Let's look at solid structures. How do the properties of solids relate to their structures and bonding? And what are unit cells? This is one thing that is not heavily covered in the AP exam, but it's something that you do need to know when you go into college. Two types of solids are found in nature. Crystalline solids predominate where the geology is slow, where the processes have taken a long time, maybe even thousands of years. The building blocks are very ordered. You see flat surfaces with specific angles, regular shapes, repeating structures. Here is an example with quartz. Quartz crystals melt all at once, and of course this is evidence that the bonds between the atoms or the molecules of silicon dioxide are the same. The second type of solid is called an amorphous solid. Amorphous means formless. They predominate in fast-setting volcanic rocks, where the ions or molecules of the substances have frozen in a disordered position. They haven't had time to migrate into low-energy positions. You have ill-defined shapes, faces, and angles. If you melt sulfur and pour it into water so that it freezes very, very quickly, you get an amorphous type of sulfur. Often you find heterogeneous mixtures in amorphous solids. Glasses, rubbers, and quickset sulfur are good examples. If you look at a pane of glass, which of course is mostly silicon dioxide, you see that it doesn't shatter in an ordered way. The fracture lines are very jagged. Amorphous solids are formed because rapid cooling inhibits the movement of ions. The ions freeze in a higher energy position. They don't have time to migrate into their lowest energy position. Out of position means that the inter-ionic distances are not regular. So when amorphous solids remelt, they don't do it at a single temperature. You don't see the kind of phase change of temperature versus time that gives you a flat melting point. Here's an amorphous solid melting. The melting curve shows the solid warming up, but then at the melting temperature you see a range of melting temperatures, and then once it's completely melted the liquid warms, giving you a graph similar to a crystal. Let's look at what's happening on the molecular level. Well, as you warm the solid, the molecules move faster vibrationally in a haphazard array. Beginning with the weakest held, which here I show by the ones that were originally farthest apart from the solid, the molecules tear loose from the array, and as stronger bonds are encountered, they will tear loose next, until finally the strongest bonds tear loose at these higher temperatures. And then finally, when they're all in liquid form, you get a liquid warming up, very much like you would see if a crystal is melting. So let's look at what we call the unit cell, which is the smallest portion of the crystal that we can determine is then the regular building blocks, so that every crystal is perhaps millions or zillions of these fundamental building blocks put together. Just as we understand gases from looking at the molecules, we understand crystals by considering these smallest units, called unit cells. Unit cells are parallelepipeds, if you studied solid geometry. First, a note on counting the atoms in a unit cell. Atoms that are in the center of the cell count as one. They're owned completely by the cell. Atoms on an edge of a cell count as 1/4 because they actually belong to 4 adjacent unit cells. Atoms on the corner of the cell count as 1/8 because they actually belong, each of these atoms belongs to 8 unit cells. Atoms in the face of a cell count as 1/2 because they belong to 2 adjacent unit cells. Let's look at some examples. Primitive cubic and body-centered cubic unit cells. This is a face-centered cubic lattice. You can see how it's named face-centered because the atoms here that are on the sides are right in the face here. Here's a face, here's an adjacent face, and we have in the middle of the cell we have an atom. Let's compare 3 cubic unit cells. The primitive cubic, as you can see here, is made up of 8 atoms or ions. The one back here is omitted. The body-centered cubic, as you see, has those 4, but also has another atom or ion in the middle. And then the face-centered cubic here, which has even more atoms in the unit cell. We've got 5 on each face. You can count the 5 here, count the 5 here, some are shared. You can count 5 up here. How many ions or atoms or molecules does each one of these have exclusively? Well, if you consider all of these are on a corner, then each one counts 1/8, and so 8 times 1/8 is 1. If you look here, you see that the body-centered cubic has 1 right in the middle that belongs exclusively to this cell, but then it has the same 8 on corners, and so it has a total of 2 exclusively held molecules. Similarly, we can show that the face-centered cubic has 4 because each of the atoms on the face, there being 6 of them, each of those atoms would count 1/2, and then you have the ones on the corner. What is the typical packing of metals? Well, the atoms are all of the same size, so we model atoms of metals with spheres of identical sizes. Structures of metals are frequently what we call close-packed. Close-packed structures are those in which atoms occupy the smallest total volume with the least empty space. Now let's consider one sheet of atoms or ions in a crystal. If you square pack them, like this, you get a certain configuration. But if you hexagonally pack them, it's easy to see that you're actually squeezing them closer together. What's the gain moving from square to hexagonal packing? Well, this is 48% empty. You can do the math if you'd like. This is only 26% empty. So when you squish these, they'll frequently look like that. Now, to visualize hexagonal close packing, you visualize the arrangement of atoms. Each layer of the crystal features atoms or ions that nest right into the next layer. You can do this with styrofoam balls or wooden balls if you'd like. You can see that these 3 would fit into the interstitials between these 6, here, here, and here. And the same thing down here, these would fit down into these little, I don't know, call them nests. Now, there are 2 types of packing related to hexagonal. If you have alternate layers in phase here, you can see one type of packing. If you rotate 60 degrees one of the layers, you get a cubic packing. These alternate layers are out of phase. This one is not right on top of this one. It's 60 degrees away. Here's another way to view that. Now the other issue is coordination number. This does not come up on the AP test, but it's something you should be familiar with. The coordination number is the number of nearest neighbors to any one ion or atom. In close packed structures, both have coordination numbers of 12. Each of these atoms has 12 nearest neighbors. It's probably easiest to consider the one right in the middle of this middle layer to see that it actually touches on 12 atoms, 3 up here, 3 down here, and 6 around the center layer. The body-centered cubic has a coordination number of 8. That's fairly easy to see here. Primitive cubic has a coordination number of 6. So summary, each sphere in closest packing has a coordination number of 12. 74% of the space is occupied. Professor Wu-Sing Yang of Berkeley proved that this is the most efficient packing in 1991. This is common for the transition metals, so copper should be packed in this way. And the noble gases, neon, argon, krypton, and xenon, when they solidify, they are cubic close packed. Helium is hexagonal close packed because that's 0.01% lower in energy. And remember, you're working now below 4 Kelvin when you're solidifying helium. Complex molecules like that of foot and mouth virus can crystallize in close packed arrangements. The body-centered cubic packing is less efficient than hexagonal closest packing or cubic closest packing. Only 68% of the volume is occupied. You have 8 neighbors. Here in this case they're at 0.87 angstroms and 6 neighbors at 1. These are found for the alkali metals, so you'd expect sodium to be packed as its metal this way. The least efficient packing of all is the primitive centered cubic packing. 52% occupied, 6 neighbors. Alpha polonium has primitive cubic structure. Solid mercury has a related tetragonal structure. Now in ionic solids, the larger ions define the ionic matrix. The smaller ions, usually the metal ions, will fit into the interstitial hole. So for instance, lithium oxide has cubic close packed oxides, and the tiny lithium ions are going to fit into the little interstices. Sodium chloride has a face-centered cubic arrangement of the chlorides. The sodium ions are kind of nice. They're much smaller, so they fit into the holes very nicely. And you can see under a microscope that sodium chloride crystals are perfectly cubic. Molecular solids, like atoms and molecules, are bonded by dispersion forces, dipole forces, and hydrogen bonds. They have generally low melting points and they are poor conductors. Most organic compounds, noble gases, and hydrogen, molecular solids. Network covalent solids like graphite, you've got the atoms covalently bonded in an extensive network. Only covalent bonding is involved. They tend to be hard solids with high melting points and generally poor conductors, but carbon has the diamond allotrope, poor conductor, but graphite is an excellent conductor of electricity. Quartz is also a network covalent solid. Here's an example of the graphite and the 120-degree bond angles we would expect. There's another picture, and here's the diamond. As you can see, the diamond is a three-dimensional network solid with 109.5 degree bond angles we would expect with sp3 hybridization. Ions, of course, are negatively bonded to positive. Electrostatic attraction is bringing them together. They are hard, brittle solids with very high melting points, and they only conduct electricity when they're melted. All salts will conduct themselves this way. Metallic solids we've studied before. The electrons in the conduction band are holding the atoms together, and they tend to be either soft or hard, all kinds of melting temperatures, depending on the electron mobility.